Okay, so notes 1-4, Extrema and average rates of change. This is going to be very similar to what you talked about in Algebra 1 when you just talked about rates of change, and with a linear function you had a constant rate of change. We're going to be looking today at things that have an average rate of change, so we're going to look at curved things that over time, or the changes in x value, they're going to have an average, not a constant, but an average rate of change. So as we start talking about this, increasing and decreasing behavior, when describing intervals on which a function increases, decreases, or remains constant. So this is talking about f of x increasing, decreasing, or remaining constant. We're always going to work from left to right, just like we read the words on a page. We want to describe what the y values are doing, whether they are increasing, decreasing, or constant, and we're going to do that by writing the x values in our interval. So the piece of the x-axis that we're going to be talking about. You'll learn how to find out if endpoints of the intervals are increasing or decreasing next year in calculus. So for right now, we'll write all intervals just using parentheses. Okay, again, no brackets, because we are not talking about regions where we have solutions or whether or not values are included in the equation or the function. So just describing intervals of increasing or decreasing, we're only going to use parentheses. Okay, as we look at the diagram below, we're going to describe the function. We're going to look at how we describe that function, increasing, constant, and decreasing. So first, as we look at this graph, reading it left to right, we see that it's increasing. Now we have an arrow here. That means that it would go down to infinity or negative infinity. So as we read the graph left to right, we would say that it is increasing from negative infinity up to -5. And the function does exist at -5, but since we're only talking about an interval of increasing or decreasing or constant, we use parentheses. Then we could say that it's constant from -5 all the way up to 0. So from -5 to 0, the function remains constant. And then from 0 to infinity, even though the graph goes to negative infinity, from 0 to infinity, the graph is decreasing. So we are talking about what the y values are doing by writing the x values in the intervals. Okay, so let's look at a couple of examples that give us equations to go along with them. So in example 1a, use the graph of each function to estimate the intervals on which the function is increasing, decreasing, or constant. Now, in the homework and in the notes, we are not going to do this second sentence supporting the answers numerically. We're simply going to not talk about that and skip that. So as we look at this first function, we have a cubic, negative leading coefficient, and raised to the third power. So we know that the end behaviors, again, just to confirm, they're doing opposite things on the ends. And as x goes to infinity, it is decreasing. So that graph should make complete sense if you understand that leading term test that you learned about in Algebra 2, and we've kind of been talking about this week. Okay, so as we read this graph from left to right, we can see that it is decreasing. And then right in here, something happens that makes us wonder a little bit. If you understand what a cubic does, and again, you could look at a table of values, it continues to decrease at a much slower rate, looks like it levels out, decreases slowly again, and then really picks up the pace and decreases rapidly once again. So this function, this cubic, is truly decreasing from negative infinity to infinity without any gaps, holes, breaks, anything like that. But let's talk about what happens here. This point, or this area right here, at 0, that is called a point of inflection. And this is where it looks like the graph kind of levels out, but we say this changes concavity. Okay, as you can see, it goes from curving upward and then hits 0. After 0, it's now curving downward. It's decreasing the entire time, but the concavity changes. Okay, let's look at B. as we look at example B, I guess I'm going to pick a different color, we're going to see that as we read from left to right, this graph is increasing until this value right here. So we have increasing y values from negative infinity up to -1. Again, we're writing the values that are on the x-axis based on what the functional values are doing. It's then going to decrease, it then turns, and it's going to decrease from -1 on the x-axis to +1 on the x-axis. Again, those values are included on the graph in the function, but we are writing intervals of increasing and decreasing, so we're using parentheses. Then from +1 rather to infinity, from +1 to infinity, our graph is increasing once again. Okay, so let's look at this paragraph down here and kind of tie everything together. We have something important to talk about, critical points. Okay, we just had some critical points, and let's talk about what they are and where they are. Critical points of a function are the points at which a line drawn tangent to the curve is going to be either horizontal or vertical. So if we go back up and look at graph B, you can see that when x is -1, you could draw a horizontal tangent line. From geometry, you probably remember that a tangent line is a line, straight line, right, that will touch a curve in just one place. And then here at -1 on the x-axis, we could draw another horizontal tangent line. So we have two critical points. We have one at -1 and we have one at +1. So as we talk about those places where you have a horizontal tangent line, you have that critical point, we have something called extrema. Extrema are critical points where a function changes increasing or decreasing behavior. So if you look at those critical points, that's where it goes from increasing to decreasing and then decreasing to increasing. So it changes behavior. At these points, the function has a maximum or a minimum, kind of like a peak or a valley, a high or a low. You've learned this in Algebra 2. This should be a little bit of review for you, either relative or absolute. So let's focus in on what we mean with those, relative or absolute. Let's break this down. So in Algebra 2, you may remember, you had absolute maxes or absolute mins. And what those may look like would be possibly vertices on a parabola. So for example, an absolute maximum may be a parabola upside down, and this value right here would be an absolute max. It is absolutely the highest point on that graph. An absolute minimum would be the absolute lowest point on a graph. Let's look at a quartic. If you had a quartic, maybe came down, curved up, it has two valleys in it, or two low points, but the very lowest point would be an absolute minimum. Okay? So those are absolute max and absolute mins. When you talk about relative max and mins would be at critical points, but not the highest or the lowest points. So let's draw some examples of that. A relative max, relative min. Put a graph on here. Let's look at a cubic. So as we look at this sketched cubic function, this high right here would be considered a relative. Whoops, that is the wrong arrow. This would be here a relative minimum. It is not the lowest point on the graph, but it is relatively a low point. It's where it changes from decreasing to increasing. So it's a relative min. This value right here, this peak, would be a relative maximum. It is not the highest point on the graph, but it is a point where it changes from increasing to decreasing. Again, has a critical point there. So those should be kind of familiar to you, absolute max and min, relative max and min. And those vertices that we see would be our critical points. Now, just going back over to this one right here, this graph that I drew over here also has a relative minimum. It has an absolute minimum, and it also has a relative minimum right there. Okay. A point of inflection, this is the next piece that we want to talk about. A point of inflection, this is what we had with the cubic that we looked at. This is also considered a critical point, and the reason is the graph is going to change its shape here. It doesn't change increasing or decreasing behavior, but it changes the bend of the curve from upward to downward or downward to upward, vice versa. Okay, so now we kind of have an idea of what critical points are. Let's take a look at these graphs right here. Okay, example 2, estimate and classify the extrema for the graph of f of x. And again, let's cross out support the answers numerically. We're not going to worry about that. Okay, so we have a function which is to the 5th degree. So we have some peaks and some valleys. So let's go ahead and classify those and estimate those. You can use a graphing calculator if you would like, but for this first one, we're just going to estimate. Okay, so this first one right here, definitely not the highest point on the graph, but it's a peak. It goes from increasing to decreasing, would be a critical point. This is a relative maximum. Okay, and there's another spot on this graph that also changes from increasing to decreasing, which is right here. And this is also a relative maximum. So this has two relative maximums. Let's approximate. So relative maximums. As I look at this graph, I can see that this first one here on the far left is maybe at -1, 2. And then this other one, we're going to have to ballpark this, maybe at 0.75 and 0.5. So maybe we'll say 0.7 and 0.5. Okay, so relative max. All right, let's look at relative mins. Okay, my first relative min, farthest to the left, would be this one right here. Kind of dips down. And then I have another low one right down here. So those would be my relative minimums. Definitely not the lowest values of the function, but they kind of bottom out. They turn from, or they change behavior rather, from decreasing to increasing. Okay, as we approximate those, the very first one, I'm going to say really looks like it's sitting right on the origin. And the second one, if we estimate that, looks like, oh gosh, the x value looks like it's maybe not quite up to 2, maybe 1.9, I would say. And then it looks like it's a little below 1, 2, 3, 4, a little below 4, maybe -4.1 if we just estimate those. Of course, you can always go to your calculator and calculate the min or the max, and then you'll have your left bound as you do the steps on the calculator, your right bound, and then it will ask you, do you want to guess? And then it will give you those maxes or mins. Okay? Okay, example 3. Approximate to the nearest hundredth the relative or absolute extrema of this cubic and state the values where they occur. So as we look at this graph, it is a cubic. It has a negative leading coefficient. So if we were to just sketch this, now I don't have my graphing calculator with me, but I do have my notes, so I can get some values from there. Oops. Okay, so negative leading coefficient, and I know that it's a cubic, so the rough sketch of this graph, it does something like this. So to the nearest hundredth, we need 2 decimal places. Whether or not it has relative or absolute extrema, that's what we're going to go find. So as I would go to my calculator and I would calculate this value right here, that is a relative min or minimum. And as I go through the steps for that relative minimum, I would find it's at negative 1.76 and negative 22.81. Then this one right here would be a relative maximum. As I look at that relative maximum on the calculator, it gave me the values of 0.43 and negative 1.93. Okay, there are no absolute max or mins on this cubic. Okay, so if we go ahead and apply the idea of Extrema to help us solve some real-world examples, we have example 4 on fuel economy. So advertisements for a new car claim that a tank of gas will take the driver and 3 passengers about 360 miles. So it will go a total distance of 360 miles on 1 tank of gas. Okay, after researching on the internet, you find the function for miles per tank. Miles per tank of gas for the car is this right here. All right, so f of x would be your result, how many miles you could get on 1 tank of gas. X is the speed that the car is going in miles per hour. And as you probably know, there's an optimal speed so that you can get the most out of your gas. Okay, so we want to find out from this equation what speed optimizes the distance the car can travel on 1 tank of gas. Okay, so we want to go to our calculators for this. And I'm just going to let you know right now, as you think about this, if you graph this in your regular standard window, you will not see a thing. You will see a completely blank graph. We have to think about what we're graphing. We're graphing the number of miles that you can get out of a tank of gas, and we're graphing the speed of a car. So as we think about this graph, we really just need to think about things in the first quadrant. Negatives really don't apply. They really don't make any sense. So as we graph this, go into this problem knowing we're going to have to adjust our window. Our x min and our x max need to change. Negative 10 to 10 just doesn't make sense. X again is our speed. So minimum speed, maybe it's 0, but we can't get anywhere on 0 miles an hour. So maybe our maximum speed, although I don't advocate this, maybe 100. So let's adjust our window, x min at 0, x max 100. And then let's talk about our y min and max. Your y value, or your f of x, represents the number of miles that you can get on that tank of gas. So y min, y max, this is the distance or the number of miles. So what would make sense here? Well, from 0 to, now they said that 360 miles is the advertisement, so that's probably pretty good. But let's go a little more than that. I actually went to 400. So if you put that in your window and then you go to look at your graph, you're going to see something that makes a little more sense, something like this. And so we have speed and we have distance. So optimal is going to be that vertex. And when we go and find that optimal speed, again, go into second, calculate. You want to do the maximum, and then you want to do the left bound, the right bound, and estimate, or not estimate, sorry, that's going to give you an exact. Your speed, your optimal speed, it will give you as 70. So 70 miles an hour, that's the best speed to get the most amount of mileage out of that tank of gas. And if you look at the distance then, the distance that you would get would be your y value, or your f of x, and that value is 362.5. Okay, so that's one way that we can use Extrema to apply to a real life situation. Okay, average rate of change. So average rate of change, again, this goes back to a concept that you learned in Algebra 1, rate of change you learned was essentially slope. There was a formula for slope, you probably remember it. y2 minus y1 over x2 minus x1. And this was when you were given 2 points, x1, y1, and x2, y2. Usually we denoted slope with an m, okay? So just reviewing all those concepts, we're going to use most of that to do what we're going to talk about here. But we have an average rate of change. So think about your test grades. If you have an average test score of 85, it certainly doesn't mean that you got an 85 on every single test. But what it does mean that you may have gotten a test grade higher and probably one lower, and then maybe 1 or 2 at 85 itself. You just don't know, but 85 would be the best representation of your tests and their scores. So when we want average rate of change, it means just that. We're going to look at these functions that have curves in them. Quadratics, which are parabolas, we'll look at cubics, and over an interval on the x-axis, there's going to be a change in the functional values. And it's not going to be constant, but what we want is the average rate of change. Okay, so this next paragraph is kind of what I've already said. Let's just repeat it. Never hurts. Remember from algebra that the slope of a line is defined as the constant rate of change. We know this. It's the same between any 2 points along that line. But for nonlinear functions, the slope is different between sets of points, so we're going to find the average rate of change, and it is basically the same. So in this gray box, you may remember from geometry, the average rate of change between any 2 points on a graph is the slope of the line through those points. But in geometry, you referred to lines through 2 points on a curve. A line through 2 points on a curve as secant lines. And that was the line that may look like this. If we had a parabola, we had 2 points on that curve, and we can see that it decreases and then increases again. So there's definitely not a constant change, but to average it out, we're going to draw what we call a secant line. That's going to determine this notation used here, which will be this. M stands for slope, SEC stands for secant, just so you can understand that. We're going to take f of x sub 2, which would really be your y sub 2, just like we remember from Algebra 1, minus f of x sub 1, which is really like y sub 1. And so then that's over x sub 2 minus x sub 1. So we still have the change in y over change in x, but now it's an average because it's not really along a line, but rather along a curve. The difference today is that you're going to actually have to go find the y values, okay? So let's look at example 5. Find the average rate of change of f of x equaling negative x to the third plus 3x on each interval. So as we look at A, from negative 2 to negative 1, these are x values. And I want to see the change in the graph, the change in the functional values from negative 2 to negative 1 on the x-axis. So we're going to start by finding the y values, f of negative 2 and f of negative 1. So I'm going to take this cubic and I will replace x with negative 2. So negative, and then negative 2, or negative 2 cubed rather, plus 3 times negative 2. This would be the opposite of negative 8 minus 6, which is 8 minus 6, and that gives me 2. Then I have negative 1. So when I replace x with negative 1, I get the opposite of negative 1 cubed plus 3 times negative 1. So that gives me the opposite of negative 1, which is positive 1, minus 3, which is negative 2. So there I found my functional values. Now I'm going to apply those to the formula. Okay, I need a little more room, so I'm going to cut this out a little bit and squeeze it down, move it off to the side. Oops, sorry, I didn't mean to There we go. Okay, so now we'll apply it to the formula. The slope of the secant line, or the average rate of change, would be the difference in my y's. I'm going to do 2 minus a negative 2 over, now I have to take the same path with my x's. I'm going to do negative 2 minus a negative 1. So in the top, I have 2 plus 2, which is 4. And in the bottom, I have negative 2 plus 1, which is negative 1. So my average rate of change would be negative 4. And there are really no units since this is just an equation. Okay, if I were you, I would pause right now and I would try to do letter B on your own and see if you can get the right answer. Okay, now let's do B. 0, 1 is my interval, and again, this is my x-axis, so these are x values that we're plugging in. And as we start to find these values, we're going to do f of 0, so negative 0 cubed plus 3 times 0, which is going to be 0. F of 1 will be the opposite of 1 cubed plus 3 times 1, so that's negative 1 plus 3, so that will be 2. Okay, so now as I do my formula, the slope of the secant line will be the difference of my y's. I'm going to go 0 minus 2 over the difference of my x's, 0 minus 1. So I get negative 2 over negative 1, which is just 2, and that would be the average rate of change. Okay, now let's lastly go to example 6, and we'll do this formula and apply it. So we're going to talk about gravity. It says the formula for the distance traveled by falling objects on the moon is d of t equals 2.7 t squared. So d of t is the distance in feet, t is the time in seconds. So time is, or distance is dependent on time. So we want to find and interpret average speed of an object for each time interval. Okay, so the first one, A, from 1 to 2 seconds. So we're going to start out by finding, oops, I should use a D, sorry, D of 1. So the distance after 1 second, we're going to plug that in. 2.7 times 1 squared will be 2.7, and that would be feet. Then we're going to do distance after 2 seconds, D of 2. So 2.7 times 2 squared, and that gives me 10.8. So as we follow our formula now, we're going to find the average speed of that object, we will take 2.7 minus 10.8 over 1 minus 2. Both will be negative, so I would get negative 8.1 over negative 1. So two negatives make a positive, and this would be, average speed would be 8.1, and that's feet per second. Okay, and I would pause right now and try to do B on your own to see if you can get that answer, and then play again and check. All right, let's look at B. So from 2 to 3 seconds, we're going to do D, keep doing F, we're going to do D of 2. Well, I just did D of 2, and I already know that it's 2 or 10.8, so I'm just going to put that right there. No need to do it again. And then I'm going to do D of 3. So I'm going to take 2.7 times 3 squared, which is 9, and that gives me 24.3. So to find the average speed, I will take 10.8 minus 24.3 over 2 minus 3, and again, I'll get two negatives, and I get negative 13.5 over negative 1, so my average speed is 13.5 feet per second. So as we can see, from 1 to 2 seconds, 8.1 feet per second. From 2 to 3 seconds, 13.5. It is getting faster. Just a little bonus for you there. Okay, and that's the end of 1.4. Good job, guys.